All right, last section in chapter 10, 10.5. This section is going to have about half the section is difficult kind of problems, and the other half is going to feel like, are you sure it's that easy? Okay, so just beware. There are two very distinctly different types of problems in this section. One of the problems is, types of problems involves the words nots. Something is going to have a word not in it, or some kind of a negation of something. And the other one is going to have the word or in it, or some kind of a joining of things, okay? So there's the distinctly different kinds that we're going to look at. We're going to start with a counting principle. This is the complements principle of counting. It tells you the number of ways, or the relationship between the number of ways something can occur and would not occur. So if we want to find the number of ways that event A happens, it's the same thing as having the number of ways any event can happen and then subtracting the number of ways it doesn't happen. So you'll recognize that notation, that A prime. We saw that notation back in chapter 2, which was our first unit. It means the complement. It means not A. We could write the same statement for the number of ways that a complement can happen. The number of ways a complement happens is the number of ways anything can happen minus the number of ways A can happen. And then a third form, all these equations are the same. That's the note here it says at the end. A third form of this equation is that we could just say that the number of ways that A happens plus the number of ways a complement happens is the total number of options available to us. These three are all the same equation, just solved for something different. All right, so we're going to do some examples using this complements principle. We found last time the total number of 5 card hands, and it was 2,598,960. Y'all remember that, right? Okay. And we want to find out how many contain the following cards. So this one says that it has at least one card that's not a club. So every time you see that phrase, at least one, we're looking at a complements principle of counting, okay? That's sort of a red flag. At least one. So it's really difficult to figure out how many ways you have at least one card that's not a club if you do it directly. Think about what you'd have to do. You'd have to find the number of ways you get one club and 4 other cards, the number of ways you get 2 clubs and 3 other cards, the number of ways you get 3 clubs, 2 other cards, the number of ways you get 4 clubs and 1 other card, and the number of ways you get 5 clubs. And each one of those would look like the problems we did last time with combinations taken multiple times. That's very time consuming. Yes? And we don't want to do it that way, right? No, we do not. There's a much simpler way to do it. We can actually look at the complement of what this is talking about. So having at least one card that's not a club means that we don't have all clubs. So this is the complement of having all clubs. So what we're actually going to find is we're going to find the number of ways we can get the hand to have all clubs. Instead of finding the 1-way, the 2-way, the 3-way, the 4-way, the 5-way, all the other options, we only have to find one thing. So what this looks like is the number of ways that we get anything to happen minus the number of ways that we get the complement that we just described to happen. And the complement we're talking about specifically here, so I'm going to write this out in words. This is the number of ways we have all hands, right? That's the 2 million number, minus the number of ways we get 5 clubs. That's very specifically what this is asking us to do. So how do we get all hands? Well, all the hands was the 2,598,960. How do we get all clubs? Well, how many clubs are there? 13. And how many do we need if we're making this type of a hand of cards? 5. So this is 13C5 at the end. We did this problem last time, the 13C5, but we'll do this as a reminder since it's been a couple days. So we have 13 factorial on top. We have the 5 factorial on bottom, and then we have to have 13 minus 5, which is 8 factorial on bottom. So the number of cards that we pick factorial, the number of cards we don't pick with factorial for combinations. So my 13 factorial, I'll keep writing my 2,598,960 out. So I'd have my 13 factorial on top. So I'd multiply the 13 down to 8, 13, 12, 11, 10, 9, and 8 factorial over that 8 factorial, and then 5, 4, 3, 2, and 1. So the 8 factorials cancel. What else is going to cancel from in here?
2 and 5 and 10.
Awesome. 2 and 5 will make my 10. And? Yeah, 4 and 3 make 12. So I have 13 times 11 times 9. 13, 11, and 9 are my numbers that are left. So let me make this a little bit smaller so I can finish it on the page underneath it. So my 2,598,960 minus. So what is 13 times 11 times 9? 1,287. Whoops. There we go. Got a random 3 in there. 1,287. And if you subtract those, what will you get? A lot, right? What's the number?
2,597,673.
So it's this number of hands that we would still have that would have this condition. So there are 2,597,673 hands of cards that contain at least one club. And there's only 1,287 that contain all clubs. Okay? The process is going to work the same way every time. Yes, Luke?
How do you know the difference, like how do you know to do either permutation or combination?
Yeah, so these are all combinations because they're hands of cards.
Okay.
So when we're working with these, you have to make the decision just like we did last time. You have to decide if whatever the context is pushes you in one direction or the other, okay? So the way we made the decision is because we decided whether the order of something matters. So the order that we get a hand of cards doesn't matter because we just rearrange them when we get them anyway. But the ordering of things that did matter were things like putting people in positions or putting houses on the lots. Those are some examples that we had seen. Yeah, and then those would be permutations. I'm hesitating a little bit, but I don't think there's any permutations within Section 10.5. I think it's all combinations. I think. Okay? If I'm wrong, I apologize, but I can't think of any scenarios where we'd have a permutation with these type of problems.
So on the slide that was your text, 11.5 is going to be all.
I believe so. If you find out when you're doing your homework that I'm wrong, send me an email real quick so that I can fix what I just said. But I believe that's right when I'm doing 10.5. Yeah. I haven't ever thought about it from that perspective before, but I believe that's right. Okay, let's take a look at another one. Our examples are all going to be about the cards just because they're easy to create a bunch of examples from. Otherwise, you guys would end up with like 4 examples instead of like 6 examples or whatever. We just wouldn't have as many. And so this is a really nice way of showing the complements principle. But you can do it with any kind of context. It's not card specific. So the examples that you have in your homework will not all be cards, okay? Okay. So this one actually says that we have, we're trying to find the number of ways that we get cards of more than one suit. So this last time where I said that phrase, at least one, and now this one says of more than one, are the same thing, right? They're telling us we're going to use complements principle. So what is the complement of having more than one suit? What's the opposite of that? Complement means opposite. What's the opposite of having more than one suit? Only one suit. So this is the complement of having one suit. Okay, so if we're going to have one suit, we have that same 2,598,960 at the front. And then we want to subtract the number of ways, I'm sorry, Jasmine, subtract the number of ways that we would get more than one suit. Well, I'm sorry, getting the complement of, to subtract the number of ways of getting only one suit. Let me get to say it right, only one suit. Well, only one suit would mean we'd have all of our cards clubs, or all of our cards hearts, or all of our cards, spades, or all of our cards diamonds. Well, we found the number of ways of getting all of our clubs to be, I keep saying it wrong now, all of our cards to be only clubs, right? It was 1287? Yeah, 1287. So there's 1,287 hands of cards that are all clubs. So how many hands are all spades? 1287. How about all diamonds? And how about all hearts? 1287. So what it actually is it's 4 times the 1287 because I have 4 suits that I'm subtracting off. There's 1287 of each of them that I get to subtract. So I have my 2,598,960 minus, and then what is 4 times 1287? I don't have this written down. 5,148. Does that look right? Fabulous. And what do you get when you subtract these two? Still 2 million something. Thank you. So there are still 2.5, almost still 2.6 million ways or million hands of cards that match this criteria. Okay. You see that phrase again? At least one. So what do we do about the at least one? We do complements. So what is the complement of having at least one face card? Huh? Nope. Good guess. What would be the opposite of having at least one face card? None. We'd have no face cards. If that's hard for you to conceptualize, think about writing out what does it mean to have at least one face card. Well, it means I could have one face card, or I could have 2 face cards, or I could have 3, or I could 4, or I could have 5. Right? What's the thing that's missing? 0. I didn't list that one. So having no face cards is going to be the contingent piece that I need for my complements here. So we have our 2,598,960, and we need to find the number of ways of having no face cards. So I didn't actually say this number in this regard when we talked about our deck of cards last time. But how many face cards were there? I did say that. There's 12. There's a Jack, Queen, and King, 3 of them of all of our suits, and there's 4 suits, so there's 12. So there's 12 face cards. So how many cards are not face cards? 40. Okay, so there's 52 cards. 12 are face cards. That means 40 are not. So this one's 40C5 at the end. You could count up the face cards, the non-face cards as well if you wanted to. Count 2 to 10. Make sure you don't forget the ace, right? And multiply that by 4. You'd get the right number as well. You'd have 40. So we have our 2,598,960 minus. Now I have 40 factorial over 5 factorial what?
35.
Yep, 35 factorial. Remember, the denominators have to add up to the numerator with those factorials. Yes, Kaden? Because we're selecting 5 cards. We still have 5 cards in our hand. Yes. Yeah, so all the ones we're doing are going to be 5. When you're doing homework problems, that doesn't necessarily hold, right? You aren't going to necessarily be doing card problems. So maybe you're talking about a committee and you're selecting 3 people. So it may be choose 3. Maybe from the certain number of people you're choosing 3. So don't let that trip you up and think that it's always 5. It's just the ones we're doing because we're doing a 5-card hand. All right, so we need to write down our 40 until we get to 35. So we have 40 times 39, 38, 37, 36, and 35 factorial over that 35 factorial. And I have 5, 4, 3, 2, and 1. So 35s cancel. Again, we have the situation where we have bigger numbers on top, like significantly right now, than on bottom. So we're probably not going to get them to, wipe themselves out completely like we did on the last one. But what are some things that we could divide by? I mean, what is a number you want to look at?
5 and 4 go make 20.
Fabulous. 5 and 4 would make 20. And so 40 would divide 20 would divide the 40 and give us a 2. My words right? I'm struggling with words today. What else?
And 3 and 2 make 6.
Okay, 3 and 2 would be 6, and you could take it out of 36. So 36 divided by 6 would be 6. That's not the only way to do this, right? Like, if you had noticed, and you could have, 5 times 4 is 20, but then times the 2 would be a 40. We could have wiped the 40 out completely instead of just kind of factoring it down. But it doesn't make any difference. You get the same thing no matter which pieces you decide to do the division, unless you, of course, make a mistake as you're doing it. But the process doesn't actually get altered. So we have a 2, a 39, a 38, 37, 6. Yeah, there we go. That's the end of it. So what do we get when we multiply out all of those values?
658,000.
Yep. And if we subtract, what do we have? Our first number that's lower than 2 million.
1,940,982.
Yep, and it's only barely smaller, right, than my 2 million. So I have 1.9 million ways that this will happen. Okay, I think there's one more, and then we're going to switch gears. We want to have at least one diamond. There's that phrase again, at least one. So at least one means 1, 2, 3, 4, or 5. The complement is none. So we would have no diamonds. Okay, so we start with the total number of ways that we can get whatever we have. Fair warning, when you get to your homework, you usually have to calculate that first number every time because the context changes every time. So we're getting that piece of these problems for free because we've already calculated it once. So if you're trying to find the number of ways that you can flip a coin, 3 times or something like that, you're going to have to figure that out every time. Okay, so that first number will change. All right, we need to get no diamonds. So how many cards are not diamonds? 39, that's right. We have 13 of them that are. So if we take the 13 that are away from the 52, total we'd have 39. And we're selecting again 5 because we're doing a 5-card hand. So we're doing 39 factorial over my 5 factorial and 34 this time. So we'll write our 39 down to 34. Okay, there are 34 factorials canceled. Tell me something else I can cancel.
535.
Fabulous. In fact, that's the only thing that the 5 will cancel with, so that's a 7 up here now. Now what?
3 and 2, 36.
Okay, 3, 2, 6. So the 36, we did that one before like that, so that works out nicely. And how about my 4? None of the numbers that are there divide evenly by 4. We've seen this happen a couple of times before, but it's been a little bit. Do you remember what we have to do when that doesn't work out?
We break it down into 2.
Right, you have to break the 4 down and then the 2s, okay? Now, if we had canceled something in a different fashion, that might not have happened on this particular problem, but it's fine that it did. We just need to break it down. So now we want to cancel some 2s out. So what would you cancel one of those 2s with?
38, 6.
Okay, so this 2 right here would cancel with the 6. I heard you say that one. That one gives me a 3. And then this 2 over here could cancel with the 38. So what's 38 divided by 2? It is 19. Yeah, not one we do all that often. So we have 39, 19, 37, 3, and 7. All right, so my 2 million number is still there. How many do I get when I do those multiplied out? It's a really fun number.
575, 75%.
It's a fun number, isn't it? I was thinking about fun numbers on the in the car on the way in this morning. My husband sent me a picture of his odometer, and it had 2s all the way across the screen, and that is 200,000 2s. Like it was like 222,222 miles. He sent it to me last week. So this is a fun number, right? It is, right? So we're going to subtract that, and if I'm remembering right, I didn't look at it carefully. I think we get another fun number in return. We do. What do you get when you subtract that? What do you get, Jasmine?
2 million and 23, then 203.
That's fun, right? Who would have thought? And so this is our number of hands on this one. Yeah, so 2,023,203. Bunches of 2s and 3s. Okay, so what we just did is the hard part of section 10.5. Okay? Now, the other part that we're doing is very, very different. Notice all the questions that we were doing there involved us finding 5-card hands. And I've warned you, not all your questions in your homework will do that, but they will have you finding multiple things, like 3-person committees, or having coins that you're flipping certain numbers of times or something like that. You're doing something multiple times. It's a multiple selection process. The process for what's going on in the next half is a single selection process. So this is called the additive principle of counting, and believe it or not, we've seen this once before. So if A and B are 2 sets, then the number of items in A union B is the number of items in A plus the number of items in B minus the number of items in their intersection. If A and B are disjoint, which means they have nothing in common, the number of items in A intersect B is 0. Then the number of items in the union is just the number of items in A plus the number of items in B. Just jot that down, and then I'll draw you a picture to jog your memory of where you've seen this.